are two basic types of electric circuits. One of them is the series circuit where the current does not split. One of them is the parallel circuit where the current splits along multiple paths. So just to show a difference of what those two types of circuits look like. For the series circuit, if I first draw a battery, and in the symbol for a battery, the longer line represents the positive terminal of the battery, the shorter line represents the negative terminal of the battery. Then we have a wire, and it gets connected to two resistors. But you notice there's only one single loop in this circuit. There's only one path for the current to flow through. So that's what we mean when we say that the current doesn't split. There's nowhere else for the current to go, and all the current that goes through one resistor must go through the next resistor. For a parallel circuit, again, if I draw a battery, positive terminal and the negative terminal, we have this wire come up, but we have this point here called a junction. And at that junction, the current is able to split. The one wire becomes two wires. And then it comes back together, so we have another junction. And back to the battery. So we see that the current is able to come up. When it reaches this junction, some of the current will go one direction, some of the current will go the other direction. And then the currents come back together at this other junction, and we have current flowing out of that point. So in a parallel circuit, the current actually splits, and some goes one way and some goes the other way. Whereas the series circuit, all of the current goes through each of the elements. So again, with the series circuit, there was just a single path for the electrons to flow from one terminal of the battery to the other terminal of the battery. And the way that we calculate resistance, the total resistance for things that are in series, this is sometimes also called the equivalent resistance. It's what one single resistor could we replace these two resistors with that would have the same effect. When they're in series, the total resistance or the equivalent resistance is just the sum of the individual resistances. So in this case, where we have resistor 1 is a 2 ohm resistor, and resistor 2 is a 4 ohm resistor, then the total would be 2 ohms plus 4 ohms, or 6 ohms. It's just a simple sum of the individual resistances. So when things are in series, the current is the same in each of the electrical devices. So if our resistors are light bulbs, the current is the same through each of the light bulbs. Again, the total resistance is the sum of the individual resistances. So if those resistors are light bulbs, it would be the sum of the individual resistances of those light bulbs. So this is what we were saying. We said that it was R1 plus R2 plus R3 plus however many we had. The total voltage is spread out across each electrical device. So we're going to see what that means in the next slide. And increasing the number of devices decreases the current, and so it decreases the voltage in each electrical device. So having more resistors increases the total resistance. If you have more total resistance, from Ohm's law, the voltage equals current times resistance, more resistance for the same voltage will be less current. And we're going to see that that will decrease the voltage in each individual electrical device. If one electrical device does not work because it breaks the path connecting the terminals, or if we were to completely remove one of the resistors without connecting a wire, joining the spots where it was connected, the current would cease. So, for example, in older strings of light bulbs, when one light bulb burns out, the whole strand of lights would go out when they were connected in series. You would have to go through and find that bad bulb and replace it, because once that bulb was out, it broke the circuit, and there was not a complete path for the current to flow, and so there was no current flowing in the circuit at all. And so to look at this example of a 16-volt battery connected to a 2 ohm and a 6 ohm resistor, the first thing is we can calculate the total resistance. That total resistance would be 2 ohms plus 6 ohms, which is 8 ohms. And so what this means is we could replace these resistors with a single resistor of the same total resistance. An equivalent circuit would be this 16-volt battery connected to a single 8 ohm resistor. And if we were to try and look at how much current was flowing, if we use Ohm's law, the voltage equals the current times the resistance, we have 16 volts equals the current times 8 ohms, or we would see that the current is 2 amps. So that means, if we go back to this original circuit, that we have 2 amps flowing here, and then all of that 2 amps flows through resistor 1, and all of that 2 amps then flows through resistor 2, and it comes out the other side. We don't lose current in any of the resistors. Again, that every electron that goes into the resistor must come out of the resistor, so we have the same number of electrons flowing by every second, so we have the same amount of current flowing everywhere in the circuit. Now, we can also use Ohm's law for the individual resistors. We could find the voltage across resistor 1 by taking the current that was flowing through resistor 1, which was 2 amps, the full current, times the resistance of just resistor 1, which was 2 ohms, which is 4 volts. If we do the same thing for resistor 2, the voltage across resistor 2 is going to be the current through resistor 2, which was the full current of 2 amps, times 6 ohms, which is 12 volts. And so if we look at this, if the voltage across resistor 1 is 4 volts, the voltage across resistor 2 is 12 volts, we can see that together those two voltages, 4 volts plus 12 volts, equals the full 16 volts of the battery. And we're going to see there's a law called Kerkoff's loop rule, where we look at the voltage gain across the battery, and it has to equal the voltage drops across the resistors when we get back to the same spot. So we gain 16 volts, we lose 4 volts, we lose 12 volts, and we're back down to our original voltage. Kerkoff's loop rule is going to be an extremely powerful tool as we go to look at circuits. And this is what we mean when we say that the voltage splits across the individual elements. Some of the 16 volts is across resistor 1, some of the 16 volts is across resistor 2. And the one that has more resistance, with the same current flowing through it, has the bigger voltage. In a parallel circuit, there are branches. Each branch is a separate path for the charge to flow. And so we have the total current coming down, and then we have the current split. And some goes one way, and some goes the other way. But because of conservation of charge and conservation of current, the total current coming into a junction has to equal the total current coming out of a junction. You see that the total current flowing in this circuit must equal the current flowing through branch 1 plus the current flowing through branch 2. When we go to add resistors together in parallel, it's a little bit more complex. And you can go through and you can look at the definition of parallel circuits being that the voltages are the same. And you can go through and you can prove this relationship. But right now I just want to state it. For resistors in parallel, to find the total resistance, you get that 1 over the total resistance equals 1 over the first resistor plus 1 over the second resistor. You need to make sure that you remember that this is not the total resistance equals 1 over R1 plus 1 over R2. It's 1 over the total resistance. And you can't just simply flip these fractions and say that R total equals R1 plus R2. That's not the way that you add fractions. You have to get a common denominator. But what we see in this, talking about the loop rule, we can see that we gain the full voltage of the battery, and then if I go along either path, we have the full voltage of the battery across each resistor, as long as there's nothing else in the circuit. This is going to be the definition for things connected in parallel. Things that are in parallel have the same voltage across them. So since resistor 1 and resistor 2 are connected in parallel, you have the same voltage across resistor 1 that you have across resistor 2. In fact, they're connected in parallel to the battery, so they each have the same voltage as the battery. For parallel circuits, a break in one path does not prevent the flow of electrons in the other paths. Let me go back and look at this. If I were to remove resistor 1, there would still be a complete path for the current to flow along. It would not be the same current that was flowing, but you would still have current flowing. There is still a complete path for the current to flow. And so the other devices are able to work independently. The total current in the circuit is the sum of the individual currents in the branches. And if you increase the number of branches, if there's more paths for the current to flow along, you're decreasing the overall resistance in the circuit. Okay, that's the part that's a little bit counterintuitive. But if you think, if there's more paths for the charge to flow along, it's easier for the charge to flow. If you think about being at a grocery store, if you have a bunch of people in one line and there's only one checkout line open, it takes a while for all those people to go through. But if you have all the people in line in one single line, but then they split off and some go through one checkout line and some go through another checkout line and some go through another checkout line, then the overall flow of people through the checkout is going to be much greater. You are able to have much more flow through there. It's the same thing with resistors. Having multiple paths decreases the overall resistance. It makes it much easier for the electrons to flow. The overall total resistance of the parallel circuit is less than the resistance of any one of the branches. And so looking at this problem, if we have a 10-volt battery connected to a 4-ohm resistor and another 4-ohm resistor in parallel, the first thing that we could do is we could calculate the total resistance. To find the total resistance, we would have 1 over the total resistance would equal 1 over R1 plus 1 over R2. We'd have 1 over the total equals 1 over 4 ohms plus 1 over 4 ohms. And so since those have a common denominator, that's 2 over 4 ohms. But again, this is 1 over the total resistance. So this means that the total resistance is 4 ohms over 2. We'd flip both of our fractions. And so the total resistance is 2 ohms. You can say that the total must be smaller than either of the individual resistors. So each individual resistor is 4 ohms. The total of 2 ohms is smaller than each of those. If I want to find the total current in the circuit, that's where we treat this as replacing these two resistors by a single resistor with a resistance of 2 ohms. So then we would have 10 volts connected to 2 ohms. And so the total current equals the total voltage divided by the total resistance, which is 10 volts over 2 ohms, which is 5 amps. So in this circuit, we have 5 amps flowing. Now, because of the symmetry, you could guess that 2.5 amps will go through one side and 2.5 amps will go through the other side. But to see this a little bit more mathematically, to understand how you would do this if these weren't the same resistances, if we wanted to find the voltage, or if we wanted to find the current through R1 only, we would first need to know that the voltage across resistor 1 is the full voltage of the battery. Again, this is what the loop rule tells us. If we start down here, all of the voltage gains and voltage drops must add up to equal 0. So we gain 10 volts going across the battery, and then we lose 10 volts going across the resistor to get back down to 0. So we have the full voltage of the battery across resistor R1. And so the current through resistor 1 is going to equal the voltage across just resistor R1, which is the full 10 volts, divided by the resistance of just R1, which is 4 ohms. And we get 2.5 amps, which is what we predicted. We said that because of the symmetry, half the current would go one way, and half of the current would go the other way. Let's look and see what would happen if it did not split evenly, if the resistances were not the same. So in this next problem, we have a 10 volt battery connected to a 1 ohm resistor, a 4 ohm resistor, and a 6 ohm resistor. And so we're going to calculate the total current, and then we're going to call the current through the 1 ohm resistor I1, the current through the 4 ohm resistor I4, and the current through the 6 ohm resistor I6. We're going to calculate each of those currents. So first, we can find the total resistance. That'll be 1 over resistance 1, which is 1 ohm, plus 1 over resistance 2, which is 4 ohms, plus 1 over resistance 3, which is 6 ohms. And so you get a common denominator. The common denominator here would be 12. So this would be 12 twelfths plus 3 twelfths plus 2 twelfths. And so we would get that 1 over our total would be 17 twelfths. Again, it was 12 plus 3, which is 15, plus 2, which is 17. So that means that the total resistance is 12 17ths. Or, if we want that in a decimal, that's the more common way to write it, that would be 0.7059 ohms. If we wanted the total current, that would be the total voltage, 10 volts, divided by the total resistance, which is 0.7059 ohms, which, if you divide that out, you get 14.167 amps. And if we want to find current 1, current 4, and current 6, we use the fact that the current through the 1 ohm resistor I1 is the voltage across the 1 ohm resistor. Again, because there's nothing else in the circuit before this junction or after the junction, we gain 10 volts across the battery, so then we have to lose that full 10 volts across the resistor to get back down to 0. So each one of these individual resistors is going to have the full voltage of 10 volts across it. So current 1 is going to be 10 volts divided by 1 ohm, so that's 10 amps. Current 4 is going to be 10 volts divided by 4 ohms, which is 2.5 amps. Current 6 is going to be 10 volts divided by 6 ohms, which is 1.667 amps. And if you were to add those three things together, I1 plus I4 plus I6, that would be 10 plus 2.5 plus 1.667, which is 14.167 amps, which you see is the same as what we found as our total current. And we have a total current of 14.167 amps flowing here, and 10 amps goes one way, and 2.5 amps goes the other way, and 1.667 amps goes the other way, and then they join back together, and we get the full current flowing. One of the things you see with this is when you have these multiple paths, current does not split equally. You have more current flowing where there's less resistance. In fact, it's inversely proportional. So if you look at the 1 ohm and the 4 ohm resistor, 4 ohms, that's 4 times the resistance of 1 ohm. So there's 1/4 the current. And so sometimes that's a much easier way of quickly solving this. If you know that there's 4 times the current through one than the other, you can quickly find that. But in general, you don't have nice, easy ratios. And so this would be the quick way to go through and calculate it. The last thing to look at is, what if you don't have just a simple series circuit or just a simple parallel circuit? Here, we have a battery, then we have this one resistor here, but then we have a junction and it splits. And so these two resistors here are connected in parallel. And so those two resistors could be replaced by one single equivalent resistor. If we did that, again, we would have this 10-volt battery. We would have this 3 ohm resistor. And then if I wanted to combine these together, we would have 1 over the parallel part so the parallel part is just these two resistors, the 8 ohm and the 4 ohm resistor. 1 over the parallel part would be 1 over 8 ohms plus 1 over 4 ohms. And so this would be 1/8 plus 2/8, which is 3/8. So the resistance of the parallel part is 8/3 ohms, which is 2.667. So now we can think of these two single resistors being replaced, or these two parallel resistors being replaced by a single resistor with a resistance of 2.667 ohms. And now if we look at that, we see that we have a 3 ohm resistor connected in series with this 2.667 ohm resistor. And so now to add resistors in series, it would just be 3 ohms plus 2.667 ohms. So that's going to be 5.667 ohms. That would be the total resistance of this circuit. If we wanted to know the total current that flows in the circuit, again, the total current equals the total voltage divided by the total resistance. The total voltage is 10 volts. The total resistance is 5.667 ohms. And so the total current that flows is 1.764 amps. That would be this current that's flowing right here through this resistor, 1.764 amps. And then if we were trying to figure out how it would split, we would have twice as much current go through the resistor that had half of the resistance. And so you would have 2/3 of it go through the 4 ohm resistor and 1/3 of it go through the 8 ohm resistor. Another way of finding that would be to calculate the voltage across just the 3 ohm resistor. That would be 3 ohms times 1.764 amps. Which is 5.292 volts. And so by the loop rule, if we gain 10 volts here, and we've lost only a fraction of it, 5.292 volts, across this 3 ohm resistor, that means that the voltage across the parallel part needs to be 4.708. That would be the full voltage of 10 volts minus the voltage across this 3 ohm resistor. That's what the loop rule tells us. We have 10 volts, we lost 5.292, so then we have to lose the rest of it to get back down to 0. And so that would be 4.708 volts. And so if I wanted the current through the 8 ohm resistor, it would be the voltage across the 8 ohm resistor, which is 4.708 volts, divided by the resistance of the 8 ohm resistor, which is 8 ohms. Which you get 0.5885 amps. If I wanted the current through the 4 ohm resistor, the voltage across the 4 ohm resistor is also 4.708 volts. And that's the definition of things that are in parallel. They both have the same voltage across them. So we have 4.708 volts divided by 4 ohms. Which is 1.177 amps. And if we look at that, that current, 1.177, is twice as much as the current through the 8 ohm resistor. Also, if I add and this current together, those two add up to the total current. Again, this can be done for any number of resistor combinations, if they're in simple series or parallel combinations. But the thing that you do is you just kind of take the circuit and you break it down and you add the pieces together. You will find the parts that are in parallel and replace those by a single equivalent resistor. Find the things that are in series, replace those by a single equivalent resistor. And then you just keep breaking it down until you get it down to one battery and one resistor. Not all circuits can be done that way. For more complex circuits, you have some things that are neither series nor parallel, and the way to do those is going to be something called Kerkoff's laws. But right now, with looking at basic circuits, a basic circuit would be a simple series circuit or a parallel circuit, or something that was a combination of series and parallel together. You can go through and you can analyze those circuits this way.